Locking Earth so that one face permanently faces the sun is a profound change in boundary conditions. Rotation is not merely day-night alternation. It is the mechanism that powers atmospheric jets, ocean gyres, and the large-scale transport of heat from equator to pole and from day to night. Remove that redistribution, and the planet's climate system must reorganize around two fixed thermodynamic poles: constant influx and constant loss. The first-order consequence is a strong lateral imbalance in radiative forcing. The day side receives continuous incoming solar flux. The night side receives none. On short timescales, local heating on the day side and radiative cooling on the night side proceed independently. But climate is not local. It is controlled by how efficiently energy can move between regions. With rotation suppressed, that efficiency collapses. The night side loses heat to space steadily while the day side traps energy near the surface. But the net planetary budget can become negative if outgoing long-wave radiation from both hemispheres exceeds the incoming energy averaged globally. That leads to the slow decline in global mean temperature observed early in the simulation. Atmospheric dynamics respond quickly. Without the familiar Coriolis-driven jets and transient weather systems, the flow becomes dominated by large-scale overturning from the hot day side toward the cold night side. Moisture evaporates relentlessly over the sunlit oceans and is advected as concentrated plumes toward the terminator and beyond. Where those flows converge, heavy, persistent precipitation forms over continental regions, the water spots that appear. They are not random. They are stationary features of the new circulation, set by the geometry of heating and the fixed position of the subsolar point. At the terminator, the interaction is extreme. Enormous pressure gradients drive fierce winds, effectively continuous fronts where hot, moist air from the day side collides with near-vacuum cold on the night side. These winds transport vapor that then condenses and freezes when it crosses into the nocturnal hemisphere. That process seeds the growth of sea ice and continental glaciers. Ice and snow increase the surface albedo, reflecting a higher fraction of incident sunlight and reinforcing the cooling in a positive feedback. On the day side, the opposite problem emerges. Intense, sustained evaporation forms a persistent, high column of water vapor. That column acts as a local greenhouse, trapping outgoing infrared and initially elevating surface temperatures. This transient retention can even push the short-term global average upward. However, two additional physical processes undermine its permanence. First, ultraviolet photodissociation of water vapor splits molecules into hydrogen and oxygen. The light hydrogen escapes more readily to space, gradually depleting available water. Second, the day side to night side transport continuously exports moisture, where it freezes out and becomes effectively sequestered on the night side. Over decades, the combination of atmospheric loss and sequestration reduces the atmosphere's capacity to retain heat. Ocean dynamics matter profoundly here, and the simulation's long-term cooling is linked to how heat is mixed vertically. In the present rotating Earth, upwelling and thermohaline circulation move heat into and out of deep reservoirs. Under tidal lock, those circulation patterns change or weaken. Surface heating can no longer feed deep ocean stores efficiently everywhere, and tidal and wind-driven mixing concentrate in different places. If deep waters are not replenished with warmth, the net heat accessible to the surface declines. All of these mechanisms combine into a multi-stage trajectory. An initial reorganization produces localized heavy precipitation and a day-side vapor dome. A temporary spike or plateau in global mean may follow. But the night side's inexorable ice expansion, increased planetary albedo, transport of water into permanent ice, and possible atmospheric escape shift the balance negative. Over decades, the simulation shows the mean temperature falling dramatically, and the system approaches a cold, steady state where the global mean is near minus 62 degrees Celsius. In such a state, oceans on the night side freeze solid, the day side is left desiccated and scorched under intense sunlight and a thinner atmosphere, and only a narrow twilight zone at the terminator retains any moderating climate. This outcome is model-dependent in detail. Timescales, exact numbers, and transient amplitudes vary with choices for atmospheric chemistry, ocean depth, and the treatment of escape processes, but the qualitative pathway is robust. Loss of rotational heat redistribution, persistent day-night forcing, terminator-driven transport and freezing, and a dominant albedo feedback that can drive the planet to a far colder equilibrium than before. The experiment shows how finely tuned Earth's current habitability is to rotation and circulation. Change that rhythm and the balance shifts toward extremes, producing a world split between steam, ice, and a fragile narrow band between them. In short, tidal locking replaces a global, rotating climate engine with a static heat pattern that enforces spatial extremes. The simulation's progression, early redistribution changes and rainfall clustering, growth of nightside ice, a transient dayside vapor greenhouse, and eventual collapse to very low global means, is a concise demonstration of how radiative balance, moisture transport, phase changes, and atmospheric escape interact to rewrite a planet's climate when rotation is taken away.